All right, welcome to class. Good to see you. It's Wednesday, our second day here. Still on chapter one, of course. A couple reminders here, quiz one, and there's a questionnaire attached to that. There's 2 pages. So do that and upload that to Learning Suite by next Tuesday. We don't have class next Monday, but you will be able to be with the TAs, and my office hours are on Tuesdays and Thursdays, so you can get help with that even next week, but be working on that. And then homework one is due Wednesday. That's when we'll finish chapter one. All the homework, is done by hand. Snap a picture, scan it, and then upload it to Learning Suite. And it's usually due on the day we finish a chapter, so you can kind of keep track of it that way. But yeah, any questions overall on any aspects? I know we weren't live with you guys last time. Thanks for watching the video. I can see the analytics of the YouTube videos and how many people watched, how long you watched, and things like that. So I could tell everybody watched the video. That's good. And people did zoom in, and we answered a lot of questions in recitation and office hours. So I think we're okay there, unless anybody has something there. You can see the outline for chapter one. We went through that last time. My outlines are pretty detailed there. That can be a launching point for you to come up with your own outlines with more details to help you keep track of the materials. So don't think that that's it though, but I do follow the book quite closely. So the topics are the same thing there. Now we left off last time with some challenges here. We asked you about carbon. Why carbon? And we had some good responses. Some people said, well, there's 4 valence electrons, okay? And that is unique in the second row. All the other atoms have different numbers of valence electrons. And that kind of makes it even then when it bonds, right? When it shares an electron to form a bond, and there's 2 electrons in each bond, right? So that's for a total of what? The magic 8 number of electrons, which is the octet of electrons. And that's unique for carbon. It's another thing though, electronegativity, and we'll see size later on. Those are really the 3 keys of why carbon is unique. And carbon, is the basis of so much in life, so many things around us, industry, fuels, who we are as living things, the biosphere, everything's based on carbon. And you should have a pretty good idea, moving forward of why that is. But yeah, those 3 things I think are the important things. Here's some organic compounds across the top here I want you to consider today. Methane, CH4, hexane, C6H14. Can you add in where all the other hydrogens are? Remember, each line represents what when we draw structures? Each line represents what? A bond, and how many electrons in each bond? 2, yeah. So anytime you see a line, any of the drawings, you can assume there's 2 hydrogen. And what about on the ends and the corners? What's there? Carbon, yeah. And then we don't always draw in the rest of the hydrogens, but yeah, you should be able to come up with 14 hydrogens here. We draw my own. And here's a very different molecule. This is glucose, blood sugar, also a organic compound, right? Carbon-carbon bonds all over the place. But we also have OH groups, alcohols. It's a polyalcohol, okay? Different type of bonding, different type of properties. Yeah, you bet. And so we want to build up this idea. What can we know about structure and bonding that will lead us toward understanding about properties and reactivity? Okay, that's what chapter one's all about. And then we have this humble little molecule right here, the essence of vinegar, acetic acid in its neutral form. It hasn't donated that proton yet. And then we have the conjugate base of that, the sodium salt. This is sodium acetate. Okay. Well, I draw those structures, but what about the properties? Let's see. Methane's a gas, very low boiling point. What about hexane? Well, that's a liquid at room temperature. And why is that? They're both carbon-hydrogen bonds, okay? But what? Hexane's a lot bigger, okay? So it has stronger intermolecular forces and can hold together and be a liquid at room temperature. What about glucose? At room temperature in pure form, it is indeed a solid material. It has a very high melting point, actually. Okay, so very different structures here. Well, why is this a solid? It has 6 carbons like hexane. Well, it might be heavier because of all the oxygens, but what else might be operating here that makes this a solid in pure form? Okay, What about acetic acid? And why is it called an acid? Well, it can donate this proton right here. It is a source of H+. The conjugate base is stabilized by resonance. Okay, what about at room temperature? It's indeed a liquid, okay, in pure form. A very obnoxious liquid, by the way, very pungent. You know, vinegar smells bad. Well, that's only 5% acetic acid in water. Imagine 100% what that would do to your nose and your mouth, okay? Much, much worse. But the properties, you know, this is a liquid. It's not a solid at room temperature, a little bit different. Maybe it's a little lighter, but it has an OH group, kind of like the alcohols here, okay? And what about this? This is sodium acetate. This is no longer an acid. This is a base, actually a weak base. But at room temperature, it's a solid. It's actually a very high melting, very brittle, salt-like material. It's ionic, right? It has point charges here. Oxygen's negatively charged, sodium's plus charged, okay? And this points out a thing about organic compounds. They can be of dual character. The carbon-carbon bond, the carbon-oxygen bond, and these carbon-hydrogen bonds, there's 3 of them there, are covalent. They're sharing the electrons. But this end of the molecule is what? Ionic. It's salt-like. The overall properties are salt-like. So you kind of have to get used to that. Inspect things by bonding and think about what that is. Ionic compounds are very brittle materials. They tend to be solids, of course, at room temperature and very high melting, okay? Very different material than this, which is a liquid, okay? So yeah, how do we figure that out with our bonding? We need to think about that. And here's the next level of understanding in OChem. What I say after structure is reactivity. And here is a reaction, right? An alkene going to an alcohol with the conditions there, sulfuric acid and water. The next level of understanding is what? Mechanism. How do we flow the electrons to get from point A to point B? Well, let's see. We have a strong acid here. And we can abbreviate that just as H+, a proton, right? Well, let's go ahead and flow the electrons here and use the pi bond. Remember, the direction of the arrow is important. That's where the electrons start. There's actually a pi bond and a sigma bond here. We need to learn a little bit more about bonding, and that's coming up, indeed, in chapter 1 here. We can pull the pi electrons out and attack here and make a new carbon-hydrogen bond right there, but that leaves behind a plus charge on this carbocation, okay? That carbon right there now becomes positively charged. We pulled out 2 electrons there. Oh, we need to talk about what? Formal charge, okay? And things can have charges. Here we've got, you know, sodium acetate, right? Well, when we react an alkene with an acid, we have an intermediate here. We don't isolate this. This is a high energy carbocation. You'll learn more about it later, the detail. Just showing you the mechanism. This is actually coming up in a later chapter, but it relates to the topics we're learning in chapter 1. Okay, why is it important to know structure? Because it helps us understand the whole shebang here, reactivity and mechanism. Well, that's not the product. What happens now? Well, water needs to attack. There's 2 lone pairs on water. And when we attack like that, we can get this intermediate, which is water with its lone pair just forming that new bond right there, right? So here I drew the arrow starting from the lone pair on water, and I attacked the carbocation. This is actually the nucleophile. This is the electrophile. This wants a nucleus. It has excess electron density. This needs a something electron-rich to attack. It wants electrons. It's electrophilic. What electrons is it getting? The lone pairs right there. So some new terms here in OChem that you'll hear over and over again, not just from me, but in the book and from the TAs and everything. Well, that's not the product. How do we get to the product here? Well, water can grab that proton. There's 2 of them on here. It's a hydronium-like intermediate. Then we get to there. Now, don't worry about this yet, okay? I'm just pointing this out as to why this is important here, okay? So bonding. How do we deal with bonding? Let's go back up here and look at the chapter outline. I already mentioned these things, and there's a big, you know, list of different topics and terms you've seen before in some context in Gen Chem. And then we left off with this. This is a picture of what? The valence electrons of carbon. And we're just looking at the 2 level here in the periodic table, right? That second level. The first level, the 1s level, is filled. Those are the core electrons. That's what? Due to hydrogen and helium. But now we're looking at the second row over, and we go over 4 spaces. That's carbon, right? Element number 6. And that means 4 valence electrons in the neutral atom. Well, what do we see here? 2s? Okay. And what are orbitals again? We need to review that. Who remembers what orbitals are specifically? Who can give us a quick definition of it? Yes, please. Very good. Region in space with high electron density. Yeah, these are particles. They have to have somewhere in space to reside. They're weird little things. We'll review that here in a second. But the 2 lowest energy ones can fill the 2s orbital. And 2 electrons per orbital, okay? And this corresponds to the lithium and the beryllium position, okay? That's the 2s position. And 2 electrons can go in there as long as they're spin paired. One is spin up and spin down. The spin quantum number is actually one of the primary quantum numbers. The first one is n, or the rho of the periodic table. Then we have what? The angular momentum, the magnetic momentum, and also the spin properties of the electrons. So they're weird little things. They're all quantized here. We have to go to the next energy level up, which is the 2p level, which is what? The main group area, boron over to neon, right? And then we have 3 more atomic orbitals, and they're the p's. That means mutually perpendicular, by the way. They're on the x, y, and z axis. Notice that they're what? Arrayed 90 degrees to each other when you superimpose them all. Okay, great. This is the atomic orbitals for an atom. Does this say anything about bonding? I've shown you some pretty complex molecules here on the board. Does this help us out at all yet? Well, be free to admit it. Not much, right? The 4 valence electrons, maybe, you can see them there. But what about the geometry? And what about the properties? This says nothing about that yet. So we need a little more information. And if you back up and look at where atomic orbitals came from, the picture becomes even less clear, I think. Except there's some fundamental ideas here, right? The nucleus is the heavy thing in the middle with the protons and neutrons. The electrons are on the periphery. These core things are quantized. These energy levels are discrete. That's not a continuous energy effect, okay? You don't turn up the gain and see the energy go up within an atom. The electrons pop out at discrete energy levels. That's kind of a weird thing. But it's a property of small particles, okay? And the attraction between the opposite charges, the positive nucleus and the negative electrons. Those electrons on the outside, if you have a bunch of them, they want to get away from each other, right? So they're arrayed further and further out from the nucleus, okay? So everything goes back to this. Let me just point out a couple things here. The Schrodinger equation, yeah, psi, very intense equation. Be glad you don't have to derive that. If you want to take a physical chemistry here in our department, you'll need differential equations in the math department. We'll teach you that too here, but it's an intense equation with Hamiltonian operators and I right here, which is the square root of -1. You don't want to go there, right? An imaginary number. Oh, that helps me out for bonding. No, not at all. The thing that helps us out is when you square the wave equation, that becomes the probability of where the electrons are found. So the response here in the class was right on. It's the location where it's found. And when we draw an orbital, it has different types of symmetries. S are spherical and P's are dumbbell shaped and they're perpendicular to each other, okay? What about the shading here? We have dark and light and the S's oscillate dark and light here. What are we talking about there? Anybody remember what that is on the? It'll become more important later on. We'll look at molecular orbitals and bringing atomic orbitals together. That has to do with what? The wave-like properties of electrons. When they propagate through space, yeah, they're a particle, but they move as waves, okay? The probability of finding it at the top, the peak, is high. The probability of finding an electron is low at the trough. And that doesn't help us out either for bonding, but when we get to pi bonds and sigma bonds, We'll have sigma and sigma star, where the electrons are brought together in phase, oscillating in phase, or out of phase, where you have constructive overlap between the wave-like properties or deconstructive overlap, okay? So we'll do a qualitative approach to quantum mechanics, okay? No Schrodinger equation, no higher math, just pictures, okay? I think we can handle that. Is that a deal? Can we stick with that? Yeah, most people are not. Oh, no, one guy wants quantum mechanics. No, okay, you're in the wrong class. Okay, no, we'll get to that later on if you want to take PChem. Couple other things here, 2 electrons per atomic orbital, 2 electrons per molecular orbital also. When we put molecules together, we'll look at MOs after we consider AOs. And Hund's rule, if they're degenerate, like the P's, all at the same level, they'll spread out. That's all Hund's rule means. And we'll get to this. We'll start to do structures and balancing the charge with the positive nucleus. They can be cations, like with carbon here. We saw the intermediate, a carbocation. Or if it's all 4 bonded, then it's neutral. If there's 2 electrons in that orbital here with 3 bonds, then it's negatively charged, a carbanion. And analogous things here with that. But let's get into this. So what do we need to look at? Bonding. So bonding, sharing electrons. We'll just mention ionic. That's the other type of bonding. You already see ionic bonding right here with sodium. How do we get to sodium cation? Well, the neutral element is sodium right there, right on the left side of the periodic table, the alkali metal. It loses that electron, right? There it is, flying off into space. No, something else is grabbing it. Let's make sodium chloride. There's all the valence electrons on chlorine. If we add this electron to chlorine, what do we go to? We go to chloride minus, okay? We have an extra electron now. Well, draw the Lewis dot. And sodium now has nothing around it, so it's plus. Why do we form ionic compounds like this? Because they now have what? The electron configuration of what? By losing an electron here on the left side of the periodic table or gaining one on the far right side of the periodic table, what do they become? What's the electron configuration now of both of these? The filled level, right? Yeah. They have the noble gas configuration. Yep. And so they're filled. At this point, we just lose the electron out of the 3s orbital on sodium, and now it has the same electron configuration as neon, okay, the filled level of 2s, okay, by losing it. By gaining an electron here, chloride becomes what? Argon, okay, and that's the filled level. That's when things are happy. The nucleus kind of collapses down, and it hangs on to all those electrons. That's the magic number to surround a nucleus of that size with that number of electrons, okay? That's why ionic bonding occurs, okay? What about covalent? Here we have CH4 for methane. How did we get there? Well, we've got 4 hydrogen atoms, and we add it to what? A neutral carbon atom. Okay, this is the Lewis dot formalism. You probably heard that term before. Gilbert Lewis was a famous physical chemist at Cal Berkeley in the 1920s. He was the first person to synthesize the idea that atoms and molecules do have electrons, but how does those actually work, and how does bonding then work? He said compounds are formed based on their tendency to want to adopt the noble gas configuration, both ionic and covalent, okay? We're not there yet. We only have 1 valence electron for hydrogen, 4 for carbon. But when we put them together, what do we get? Okay, now you've seen this before, hopefully, but where's the noble gas configuration now? Why is methane a happy molecule being CH4? Yeah, look at carbon, right? Circle those electrons. There's your octet, your 8 electrons. It's happy now, okay? Stable molecule. What about hydrogen? Well, it's not 8. It's a first row element. We call it a duet of electrons. So there's no quartet, there's no trio in chemistry. If you're thinking about string quartets or groups, you know, nature prefers a duet or a octet, okay? And that's just the size and shape. the balance of the electrons there around that. Let's see, let's do some a little more complicated ones maybe. Well, maybe let's, balance out the others here. So boron has 3 valence electrons. My dots there are important, right? And when boron forms 3 bonds, it leaves behind an empty orbital, okay? That makes it very reactive. Why? Because it's not an octet yet. It's highly Lewis acidic, okay? Which is a difference with carbon. Carbon, when it forms its 4 valence, bonds here for the octet, is much happier than boron compounds. Why? Because this leaves behind an empty orbital, okay? And let's do nitrogen and oxygen. Yep. So here we have nitrogen, 5 valence electrons, right? Plus 3 hydrogens, or 3 other bonds it can share electrons with. Why am I saying 3? Oh, you should wonder. Here I had 5 valence electrons. Why not 5? Well, let's figure it out. Let's do the experiment. So what would this be? 3 bonds to nitrogen. Oh, that's the octet. Okay. But we have what here? We have a lone pair. And that's the non-bonding electrons, but it's part of the octet, which makes what? Ammonia and amines stable molecules with 3 bonds. Well, why not 5? Whatever here. 2, 3, 4, 5. I can draw it. It must be able to form, right? What's wrong here, though? Come on, I know it's early in the morning. What's wrong with 5 bonds to nitrogen? Breaks the octet rule, right? How many total electrons are shared now around nitrogen? Remember, each bond is what, 2 electrons? This is 10. You can't fit 10 electrons around this small of an atom. So this is an imaginary molecule. Sorry, you'll lose points on the quiz or the test. We stay behind with 3 bonds and 1 lone pair, okay? What about oxygen? 1, 2, 3, 4, 5, 6. 2 hydrogens. And we go to 2 lone pairs and 2 bonds. So there's our octet again. Not 6. We're not forming 6 bonds. 2 bonds with 2 lone pairs. Does that make sense? Simple bonding. Hopefully that makes some sense. Now let's get to the OChem part here. Let's make this a little bit trickier, right? How about instead of CH4, let's go to something a little trickier. How about C2, H6? Oh, now that's the empirical formula. That's just the ratio of atoms. The molecular weight can be figured out there. But that says nothing about bonding yet, okay? How do we figure out bonding? And we've got 2 carbons now and an oxygen. We've got 3 heavier atoms, then a bunch of hydrogen. How are we going to deal with this? Well, we start with our carbons, right? We got 2 of them. Start with our oxygen. And don't be shy about doing the dot thing. You're a molecular accountant. We keep track of everything in OChem. We're control freaks in chemistry. We want to know where everything is and what's happening. And, practice that. Make sure you know where that is. And then what? The 6 hydrogens. Okay. Start with the heavy atoms first. Let's link together 2 carbons. Let me get to that. And so what's this now? That's just sharing it. Okay, I'm not putting 2 dots there between the 2 carbons. You know what that means now, right? 2 electrons. We're sharing that. And let's put the oxygen on there. So there they were, 1, 2, 3, 4, 5, 6. So there's a lot of dots on this board. Sorry, hopefully that. Okay, so put the heavy ones in first. And now what? Put the hydrogens in. So let's see, what would we come up with? C6, hydrogen, 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 hydrogen. And oh, what about here? Well, 2 lone pairs, just like water. And then hydrogen. Oh, there's our alcohol group. Okay. You've learned a new functional group today. You've heard about alcohol before. There's a lot of types of alcohol. There's wood alcohol, grain alcohol, isopropyl alcohol, rubbing alcohol. A lot about alcohol. There are alcohols in glucose, the sugar molecule. They're all over the place. But this is one molecule, so count them up. 1, 2, 3, 4, 5, 6. Yep. And we can draw it like that. That's the stick figure for it. Here's the the structural formula for it. That's a little unwieldy. We like these structures, but make sure you know what that is. 2 hydrogens there, 3 hydrogens there. Is there another way to put together C2H6O? Anybody come up with another way? How else could we do this? Yeah. Very good. Put oxygen in between the 2 carbons. So let's just go ahead and do that. There's our 2 lone pairs. And then where do we put the hydrogens? Oh, right there. Okay. We have 2 methyl groups on the end now. Okay. Or we can just draw it like that. That's no longer an alcohol. That's an ether. And guess what? Your simple bonding analysis here coincides with what's actually known about these molecules. This has a very high boiling point. The boiling point of ethanol here is 76 degrees Celsius. That's 170 Fahrenheit. Very high boiling. Not as high boiling as water, though. Water, what boils at 100 degrees C, right? So even though it's heavier, it's lower boiling. We need to think about that too. What's the difference with water? And then this guy, ether, that boils at 25 degrees C. Wow, the ether is much more volatile, we say. There's something else here about intermolecular forces that's different. We're not talking about those forces yet in chapter 1, but anybody have an idea why ethanol is higher boiling than dimethyl ether? Usually someone's right on it, yeah? Hydrogen bonding, very good. When we talk about intermolecular forces, almost every answer can be hydrogen bonding. So yeah, keep that in mind. We'll see that later on. This one is a hydrogen bond acceptor, but this one's a hydrogen bond acceptor and donor, okay? So that's a little more details there, but the order of the bonding is the important deal there, and yeah, how we can do that. Let's do multiple bonds here. How about another formula, and still Lewis dotting, and that's okay. How about C2H4? Now, it may seem like a step backwards, but it's something important structurally we need to talk about. Let's put the 2 carbons together like we did, and let's put 2 hydrogens on each carbon. What do we have left over at that point? 2 more valence electrons sitting there. What are we going to do with those for C2H4? Make it a double bond. Let's share them right there. And look at that. I'm showing the mechanism. Now, that's not how an alkene actually forms. But conceptually, that's how you can think about it, right? We dump those electrons in, and we come up with this, which is doubly bonded now. Well, wait a minute. We needed to back up and do this one first, right? C2H6. This is ethane. And what does that look like? Well, that's where you have the 2 carbons with the 2 methyl groups on the end. Okay, there I'm adding them all in. Ethylene, C2H4, is very different reactivity and structure-wise than ethane because of the double bond. Very good. And we'll see later on with MO theory, there's a sigma bond here and a pi bond. That says something about the geometry of that. Hybridization here, we'll get to that too. These are sp3 hybridized if they're alkanes, if they're bonded to 4 things. Bonded to 3 things here, that's sp2 hybridization. So I'm kind of throwing in the topic right at the end of chapter 1. Those of you who have read ahead will be richly rewarded in that content. If you're confused about sp3, sp2, sp, don't worry, we will go through it carefully and you'll see it. This is for methane and the tetrahedron. If you had another methyl group here, that would be what? Ethane, okay? And here's the double bond for ethylene. And you see the pi bond here, both the red and the blue, and we'll talk more about that later and what that means. That means 2 p atomic orbitals, the 2 pz's interacting sideways. The sigma bond right in the middle is from an sp2 hybrid orbital on carbon pointing right over at this one. And by sigma, we mean the electron density is right on the axis between the 2 atoms. Pi bonds, the electron density they're sharing is off the axis. And then we have the 2 hydrogens on each carbon on the side. But that's a flat molecule. All 6 atoms here are flat, trigonal planar. Okay? So that kind of combines Vesper and MO theory, but we'll go through that in detail too, don't worry. But Lewis dot gets us on the right path, right? What's the next one we need to do? We need to do, what? C2H2. That molecule is also known. Anybody know what C2H2 is called? Anybody done any welding? This stuff burns at 2,600 degrees. What is it called? Acetylene. Acetylene torches can cut through metal. Okay, you knew organic molecules were powerful, right? Here's a very powerful one when this guy combusts. But what is it? Okay, so we got carbon with carbon. And let's add in the 2 hydrogens. And what do we have left over? Well, 2 electrons on each side, and you can see where we're going here, right? So dump them in, and what do we get here? We get a triple bond. So we have the hydrogen, carbon, triply bonded. It's diagonal geometry. It's only bonded to 2 things, the other carbon and a hydrogen here. It's sp hybridized, and the bond angle here is 180 degrees. We'll get to that and everything, but it's a consequence of how that is. Oh, what about the triple bond? What is it? Well, it's a pi bond, and a sigma bond. And here it is. Okay. This is why we bring these models right from the get-go. These are the important topics of structure in OChem, right? Here's the 2 carbons where my fingers are. Here's the sigma bond between the 2 carbons. It's sp hybridized, pointing right at each other. And what's left over when you just mix the s and 1p, you leave behind 2 p's. Remember there are 3 p's? These are the p atomic orbitals that are not hybridized. We don't mix all of the atomic orbitals when we do this jazz, okay? So we've got 1 pi bond here, where my hands are, and perpendicular to it, and that's the geometry of those p atomic orbitals, right? The other pi bond, there's 2 of them. And that's where the reactivity will be. Okay, it's very important to know where there are questions on this. But again, we're just focusing on the Lewis dot aspects right now. We'll get into more of the hybridization and the geometry.
I was just going to ask about the actual figure. So, just the diagram, whatever, to show. Are the yellow?
Oh.
Are they bonding?
Oh yeah. Question on the model. What's the coloring here? That's the shading, the sign of the orbitals. That does not refer to any charge. It's the wave-like properties, the peak and trough. These 2 are brought together in phase. It's actually technically in the math part of the Schrodinger equation. It's actually the sign of the wave equation. If they're both positive, you get the constructive overlap. If you do the Schrodinger equation, bringing them together out of phase, then you get the shades opposite of each other, and it's the anti-bonding orbital. But we'll get into MO theory and nail that down. But it's a good thing to worry about right now. Okay, so as you're reading chapter 1, keep that straight. So yeah, so we got alkane, alkene, alkyne there with the different things. Let's do a harder one here. C2, we still just have 2 O2, H4. Take a minute right now and try to come up with a Lewis dot structure that's neutral, that's got the octet for everything. Start with the heavy atoms first and then sprinkle in the hydrogens. And if you have leftover electrons, dump them into what? Double bonds, okay? So even though the concept's relatively straightforward, I think, you're just keeping track of electrons, valence electrons only, please. If it was charged, then we'd have to lose an electron if it's a cation, or gain an electron if it's an anion. Okay, quiz 1 actually has a little exercise with that. But let's see what we come up with here. If we've just put them all together, you get something like this. Okay, and if you can put in the hydrogens here, and double bond there to get that one, and then need another hydrogen there on that carbon. And 1 there. And you can add in your lone pairs on oxygen if you want. Anybody come up with that one? Was that one you came up with? Okay. Maybe? Okay. I see some heads nodding. How about if we have the 2 carbons together here and then the oxygens here? There's a couple of things we could do there then. We could have a double bond between carbon and oxygen. That's called a carbonyl compound. With a hydrogen here, that's actually an aldehyde. And then what else would you need here? Hydrogen there. Oh, there's our old from alcohol again. Okay. And then what? 2 hydrogens here. And double check your work. 1, 2, 3, 4 hydrogens. Yep. And everything's octet kosher, I think. So that's one way to do it. Anybody come up with some other ones? How about this one? Is that also C2O2, H2? 2 also? Yeah. Are there others? Yeah, there's actually a ton of them. How about this one? Oh, we just talked about that one, didn't we? That's the molecular formula of acetic acid. Is that right? Yeah. So this the 4 electrons there. Wait a minute. Yeah, yeah, that's right. This one's right too. Right, you have the 2 there, and then you have the 3 out here, right? And then the 1 right there. Anybody come up with some other ones? I've got a couple others here. How about this guy? How about a 4-membered ring? The possibilities are endless. That's the rub of OChem. Sorry, even with a simple molecular formula, you have many, many choices of how molecules are made. There's many known molecules for C2H4O2, okay? The structures can propagate even more when you have more carbons here. So the order of bonding, but these all have different properties depending on what type of functional groups they have, and that's another thing moving forward there. So I think that's okay right there. Let's finish up with formal charge now. Unless you had questions on that. I'm sorry, I didn't want to go too fast. Most people were nodding their heads when I made a couple. See if you can come up with some more for that, okay? How about formal charge? We had acetate there, and we had a charge, what, on oxygen, negative charge. We have the plus charge on sodium. You should be comfortable with metals being positively charged, right? They're on the left side of the periodic table. They can give up 1 or 2 or more electrons and become cations, right? That's what metals do. They're great at being cations. Their metallic form, you know, it's the shiny stuff. They conduct electricity, but that material tends to oxidize quite readily. Unless you're a late transition metal and you're more stable being in the 0 oxidation state, like gold, platinum, palladium. Silver oxidizes still. Copper oxidizes slowly too, right? So they tend to want to be in higher oxidation state, losing electrons, because they're on the left side of the periodic table. Main group elements, and carbon being right in the middle is unique, right? It can gain or give up electrons or share the electrons, right? And those are the stable forms there. We need to say more about that when we get to electronegativity, but the last topic I think today is formal charge. Let's look at this molecule. Just as it's drawn, NH4, is something missing here. There's no lone pairs on that, okay? So let's examine the bonding here. 4 bonds to 4 hydrogens. What's the charge on that nitrogen then? +1, yeah. Now how did we get that? Formal charge equals the valence electrons minus bonds minus, or plus in this case, this is outside the fence, plus lone pair electrons. Okay, and counting up all the lone pairs. So this is the bonds it's sharing, and this is the bonds it's not sharing. The book has a little bit different formula. It says the unshared electrons and then half of the shared electrons. In this, you subtract from the valence electrons. You get to the formal charge. And this is just bookkeeping, keeping track of the balance of the positive charge of the nucleus and what? The loss or the gain of electrons. And they're in the bonds, okay? So that's how we analyze it. So looking at this nitrogen volume, how did we get this plus here? For nitrogen, and that's what we're looking at here, 5 valence electrons minus how many bonds? 4, and then no lone pair electrons. So yeah, that is, that's what? +1, okay? How about this? CH4. Very different now, right? 4 valence electrons, 4 bonds, no lone pairs, 0 on carbon. Okay, so if you see 4 bonds to carbon, you're safe there. Let's look at acetate again. And here I'm drawing all the lone pairs in there. And if we give you a structure without, and then ask about the formal charge, we'll show all the electrons, including lone pairs, okay? So here's all the lone pairs drawn on acetate. Is that the correct structure, though? Is there a formal charge here in the molecule? And by formal charge, we mean it can be centered on an atom or it can be delocalized within the molecule. We need to get to resonance coming up. And actually on Friday, we'll get to resonance. Another thing about bonding. But seeing the lone pairs here, let's look at this oxygen here. 6 for the valence electrons minus how many bonds? 1, 2. Count both of them, the pi bond and the sigma bond for a double bond. And then how many lone pair electrons? 1, 2, 3, 4. So what's the charge of that oxygen in the carbonyl? 0. Yeah. Okay, neutral. What about this one? Different oxygen, right? 6 valence electrons. How many bonds? 1. How many electrons shown on here? 1, 2, 3, 4, 5, 6. So what's the charge here? -1. Okay. It would be neutral if it had an odd electron there, if it only had 5 non-bonded electrons. But it has 6. It has the 3 lone pairs. What about this carbon right here? 4 valence electrons. Remember, you switch it for what atom you're talking about. How many bonds? 1, 2, 3, 4 bonds. Any lone pairs showing on that carbon? Nope. So again, 0. Same thing here. We're not drawing all the hydrogens. You need to add those in. How many hydrogens are out here on this carbon? 3. Yep. And so what's its formal charge? 0. Okay. So overall, acetate has a negative charge. You need to put that charge there, okay? And overall, ammonium needs a plus charge on it, okay? So you should be able to go through a structure of a molecule and seeing where things are and determine what type of charge might be where on it. Let's look at this diagram back up here real quick, Gannon. And what do we see? Carbon can come in 3 varieties here. The stable one is where it's neutral and 0, right? If it only has 3 bonds and no electrons here, that's a carbocation. You saw an intermediate mechanism I drew earlier, right? If there's 2 electrons there, it can be a carbanion. Now these are very unstable. This is violating the octet rule. This only has 6 total electrons. It's Lewis acidic. It wants to react with something electron rich. But it can be an intermediate. We don't isolate it, but it's there, carbocations. You'll learn a lot more about carbocations, okay? Carbanions are very basic. They want to be protonated right away, okay? They're very electron rich, but they're octet okay, right? There's 8 electrons there, but they're negatively charged. And the nitrogen, it switches over, right? 4 bonds here because it only has 5 valence electrons, different than carbon. When it has 4 bonds, it's cationic. If it has 3 bonds in the lone pair there, it's neutral, right? So these fundamental things here, you should be comfortable with there, and I won't go through all the other ones there. Oxygen also, here's what we've been talking about with water and the alcohols, 2 bonds, 2 lone pairs. If you have another bond and just 1 lone pair, that's cationic. That's an oxonium cation. And you have the anionic form of oxygen. Where did we just see that? We just saw that in acetate, right? Okay. So keeping track of these fundamentals is very important there. Okay, let's say one more thing about this. These guys have different properties, right? Same molecular formula, C2H6O. What do we call these? We put the order of the bonding together differently. What are we going to call these? As a name, it starts with an I. What is it? Isomers. We're going to see a lot of different types of isomers. Iso meaning closely related, but mers of each other different. And this is different order of bonding. And it's a consequence of the Lewis dot, how you order them up. This is very volatile, low boiling point, very high boiling point, stronger intermolecular forces. We'll see a lot of other isomers. We'll see conformational isomers where we rotate around sigma bonds. We'll see stereoisomers as well, okay? But the same molecular formula, different construction. We're going to call these constitutional or structural isomers. Okay. I think your book uses constitutional. Structural isomers is fine too, but it involves different orders. Same empirical formula though, right? Same number of atoms, just different bonding and then different properties. And wow, very different properties, very different type of reactivity. Let's see, resonance structures. Let's do a little bit on resonance structures. We've been talking about acetate, and resonance structures are important here. And let me give you some data first on this. A carbon-oxygen single bond right here can be determined very accurately, its bond length, by X-ray diffraction techniques. And the length of a carbon-oxygen single bond, just a sigma bond there, is 1.43 angstroms. And an angstrom is 10 to the minus 10 meters in length. So about as tiny as you can get. But X-rays, their wavelengths are the same distance as a typical bond at that geometry. And so you can very accurately get these numbers, okay, if you do X-ray analysis carefully. And then a typical double bond here between carbon and hydrogen. This is formaldehyde, actually. And if you get that distance right there, it's 1.20 angstroms. It's shorter, and you should be thinking about that. It's a carbon-oxygen bond. Why is it a different length than a sigma bond? Well, this has a pi bond and a sigma bond. But let's look at acetate again. If you measure that bond and that bond by X-ray, they're both the same, and they're both 1.25 angstroms. But we're drawing this, right? So there's a limitation here. Is that really a single bond? Well, it should be longer. Is this really a double bond? Well, it should be shorter. Okay, but they're both the same when we do the X-ray analysis. So what's up with this? Well, there's a limitation to the Lewis dot structures. So we've moved on from Lewis. He's very good at keeping track of the electrons and the type of bonding. But when we have the potential to delocalize these electrons, we have a limit. So let's say we can form another structure here, and I'm using a double-headed arrow. Let's take the lone pair here and dump that in and push this pi bond electrons out here. And notice I'm using double-headed arrows. I'm moving 2 electrons at a time. And what am I getting? I'm getting, oh, the same thing. Wait a minute. Dr. Andrus has just gone crazy, hasn't he? He's drawn the same structure. But what did we do? We exchanged the single bond and the double bonds, right? In fact, these are resonance structures, localized structures, but in reality, the electrons are delocalized, okay? And that's kind of the key here. If you delocalize the electrons, you create a hybrid, a combination of the 2 localized resonance structures. And the actual structure looks like this, right? And so it's a limitation there of the Lewis dot structure. Really, both electrons are sharing that negative charge, and that's equalizing the bond lengths, right? But we draw it like this, and this is octet okay, that's octet okay. So don't dog on Lewis too much. He had the right idea, but there were limitations to his model. Didn't take into account that if you have excess electron density next door to a pi bond, you can actually push those electrons out and create another structure. It's degenerate in this case. Not all resonance structures will be degenerate. We'll pick it up there on Friday. But it's an important idea. These are localized Lewis dot structures. This is the hybrid, which is more in tune with what we see experimentally. Those bond lengths are the same, and they share the charge in both spots. Is that okay? I know that's kind of a fly in the ointment. You think you get this figured out, and then we throw you yet another thing that challenges your understanding. But don't worry about that. The picture will hopefully come into focus here, and we'll apply all these things with organic examples and help you out there. But I think we're done for today. We'll see you next Wednesday as things kind of even out, okay? And if you really want to come in person on other days, I think we'll let you do that. I see there are some empty spots. But email me if you'd really like to come every day, and we can accommodate that. Most people prefer to watch the videos later on and don't have to wake up at 6 in the morning. That's why we've done this hybrid this way. We've given you these options that way. So very good. We'll see you next week. Okay.